Hello again. In this video, we are going to continue our journey to move our robot in a more autonomous way. In particular, we're going to see how can we drive our mobile robot from one point in our environment to another. This is what we call point-to-point navigation. Now let's recall our setup. Let's consider a mobile robot that is moving in a two-dimensional environment. It's always useful to consider a coordinate system in this mobile environment that helps us to identify different parameters, such as the robot pose, which represents the robot position in terms of the x value, the y value, and its orientation or its heading with respect to the x-axis. And we can put all of these parameters into a vector that we call pose. Now, in order to control this robot, let's assume that we have a differential drive robot, and the control signals are the linear velocity of the robot, which determines how fast the robot is moving forward, and the angular velocity of the robot, which determines how fast the robot is turning either clockwise or counterclockwise. And we denote these two different velocities by Vx and omega. Finally, we have the goal. It's a predefined point in our coordinate system that is represented by gx and gy, and the aim of this exercise is basically to identify the control signals, the linear velocity and the angular velocity of the robot, such that the robot is going to drive from its current pose all the way down to this goal. Now let's consider a very simple case here, where the robot is directly in front of the goal, so it does not have to do any kind of turn. In other words, our angular velocity of the robot is going to be 0, and the only thing that we have to control here in this particular case is the linear velocity of the robot, because we only have to drive forward to reach the goal. Now the question here is, what kind of control signals should we use to produce this result? And one way we can do it is use something called a bang-bang control, where we set the linear velocity of the robot to a fixed value denoted by Vmax here, and we maintain this distance until we get close enough, or the robot pose is close enough to the goal. And we can determine or define this idea of close enough by measuring the distance between the robot and the goal using the Euclidean distance formula that we have here. And as long as that distance is greater than some epsilon, which is just a number that is defined by the user, we just drive the robot at that fixed velocity Vmax. However, when this distance is less than or equal to our epsilon, then the robot stops. As I said before, this kind of control is called the bang-bang control because it goes from one maximum value to one minimum value abruptly. There is no gradual change over time. Now let's consider a second case where the orientation of the robot is not aligned with the goal itself. In other words, that there is an angle that spans the area between the robot heading and the goal with respect to the robot itself. And that angle, which is denoted by alpha here, can be computed using this formula, which where we have the arctan of the distance between the wall and the goal, and we subtract the heading of the robot. And then one thing that we should notice here is that this alpha angle is always between minus pi and pi. One thing to point out here that in general arctan returns a value between minus 90 and 90 degrees. However, with a small tweak, we can make it return a value between minus pi and pi, and in this case we use something called arctan 2. Feel free to Google it and find out how arctan 2 differs from arctan. Now, once we have that angle between the goal and the robot heading, we can use that to determine our angular velocity of the robot. And the way that we do so is by using this formula over here, where we first normalize our alpha and dividing it by dividing it by pi, such that we have a value between minus 1 and 1, and then we multiply that value by a maximum angular velocity that we define beforehand. And this kind of controller, we call it a proportional control, and the reason why it's called a proportional control is because our omega, our angular velocity, depends, or its value depends directly on the value of alpha. It's proportional to the value of alpha. Okay, so now we have these two cases. We can combine them together to get a general case where we can compute both the angular velocity and the linear velocity of the robot by first measuring at each time step the angle alpha using this formula here, and also the distance between the robot and the goal. Then we use these two values to compute our angular velocity, just as we had before, using the proportional control, and we can compute our linear velocity using the band control. Great. Now, so far we have only considered the case where the robot is moving to the goal in an empty environment, but that's not very realistic. Most of the environment that we have, there are some obstacles, there are some areas where we don't want the robot to hit, like forbidden areas, like a wall, for example. And in this case, we need to make sure that the robot does not hit that particular obstacle for its safety, and also maybe that obstacle is a human being or a person or a living thing that we don't want to hurt. So in this case, we need to make sure that we are avoiding these obstacles. So there are two different things that we have to, in order to solve this problem, we have to consider two different cases. We have to make sure that the robot is going to the goal, and at the same time it's avoiding obstacles whenever it finds it. Okay, so in our Puzzlebot, we have equipped our robot with a sonar that is mounted on the top of a servo motor, and the servo motor can be controlled by an angle that we feed through our program. Now the question that we have to answer first is, how should we select that angle of the servo? Should we, because we cannot point our sonar at all different directions at the same time. We have to be quite smart about it, and one way to do so is by considering our path in the past. So if the robot, for example, is turning counterclockwise, it might be more useful to orient our sonar in that direction as opposed to oriented in this direction, because we don't gain any information by looking at this area. Likewise, if the robot is turning on the other direction, like clockwise, we probably need to turn our sonar in that direction. Now, the formula that we have over here basically represents how can we compute the angle of the sonar, which we denote by the Greek letter gamma. And again, it's the proportional controller that uses only the angular velocity of the robot, where we normalize it by our maximum angular velocity and multiply it by by the maximum value that the sonar that the servo can take, which is gamma max. Now, you might observe that I am not using the linear velocity of the robot, because from the control laws that we've used so far to drive the robot from one point to another, the linear velocity of the robot is usually fixed. It's either a Vmax, maximum velocity, or 0 when we are close enough. So it doesn't change over time. Therefore, it doesn't give us more information. It doesn't help us in identifying the best angle for our servo motor. Okay, so now we know how to place our servo. The next question is, okay, what do we do next? One of the things that we do is, like, as soon as the robot detects something in front of it, or something that is close enough to it, it needs to do something. It needs to avoid it. So how do we, what kind of strategy should we use to avoid this particular obstacle, and also make sure that we go to the goal eventually? One way to do so is do what we call follow the wall or follow the obstacle. And in this case, the way that we can follow the obstacle, there are different strategies to do so, and one of them is to fix the angle of the servo to a particular side of the robot. In this example, we are fixing it to the right side of the robot, and then we use and then we can fix our linear velocity as we have before, and then we can use what we call something similar to a bang control, where we compute this value c, and I'm going to explain why we use this particular formula, and then after that we have 3 different conditions for our angular velocity, where so we have this row over here. It represents the value that we get from the sonar. It's just a distance, and if that row is less than some minimum value, we're going to use this c, or the negative of that value, as our angular velocity. If it's greater than some maximum value, we just use that c, and if the row value, or the value that we get from the sonar, falls between row min and row max, we just fix our omega such that the robot is just going straight. Now let's try to dig deeper and try to understand how this thing works. Now if you take a look at c, or this value over here, it's omega max multiplied by sine of gamma. Now the sine function over here is always going to return a value that is either -1, 1, or 0, depending on whether this gamma is positive, negative, or 0, and we multiply that by omega max. So c in general has 3 values. It can be positive, negative, it can be either positive omega max, negative omega max, or 0. Now if you take a look at this situation that we have over here, our gamma represents the angle between, if we assume that we have a coordinate system on the top of a robot where this is our x-axis and here's the y-axis, then the angle of the servo is always going to be a negative angle. So gamma represents the angle here, and the sine of that angle is going to be -1. We multiply -1 by omega, so we have minus omega, which equals to c. Now assume that gamma or rho here is smaller than rho min, so it means that this condition is going to apply, and in this case we have minus c times minus number is going to be positive omega max, and omega is equals to positive omega max, which means that the robot is going to turn counterclockwise away from the obstacle. Right? So if it turns away from the obstacles, of course, in this situation, rho is going to increase over time, and if it gets much bigger than rho max, then what happens here is we're going to consider this condition instead of the top one, and omega is going to be minus omega max, because gamma here does not change. We don't change the angle of the sonar when we are following the wall. And in that case, the robot is going to turn clockwise. Now, the reason why we have the third condition here is because we want to minimize the oscillation of the robot moving counterclockwise to clockwise, and we just have a small band where the robot just goes straight for a bit, and then if it gets bigger than the max, it goes clockwise. If it's less than rho min, it goes counterclockwise. Okay. So we're going to follow this wall, but we need to make sure that we are not going to follow it indefinitely. We need to exit this wall following routine to make sure that we are still following, we are still going to reach our goal. And to do so, we can always, in each time step, we can check the angle alpha, which is the angle between the robot heading and the direction of the goal with respect to the robot. And if that angle, or the absolute value of that angle, is less than some threshold value, we denote it by epsilon 2, for example 15 degree angle. In this case, we exit the routine of wall following and we go back to point-to-point navigation. Now, this transition from the wall following to point-to-point navigation and vice versa can be implemented easily using state machines. Okay, let's now move to MATLAB, and let's see if we can implement this point-to-point navigation with obstacle avoidance and see if it works in simulation and in reality. Okay, so here in MATLAB we create a new file, we call it drive to a goal, and it has the same format that we used before to create all of our algorithms so far to control the robot, either in simulation or in reality. Remember that this small if statement over here is used to initialize different parameters that we're going to be using later on in different time steps, and we start with defining the DC motor signal mode, and in this case we're setting an omega set point as opposed to voltage PWM, and we're also making sure that the servo angle is set to 0. Then, because we need to know where is the position of the robot at each time step, we need to create a localizer, and as we defined it before, we just use the localization class. Make sure that the initial pose is always set to the origin 0, 0, 0, where you have the x value, the y value, and the theta. If you decide to change that to something else, either in simulation, make sure that you change it here as well. Then we define some maximum parameters that we're going to be using, such as our maximum angular velocity or maximum linear velocity. Both of them are defined in radian per second and meter per second respectively. Then we have to define the safe distance in meters, which is basically the value that we use to determine whether a particular obstacle is close enough to the robot. And we also need to define the maximum sort of angle. This is a physical limitation based on the servo motor that we are using, and the one that we are using in Puzzlebot has a maximum servo angle of 40 degrees. We also need to record the wheel radius of the robot as well as the wheelbase, which is the distance between the two active motors or active wheels. You can read these parameters directly from the robot object that we have here, or you can just measure it and write it manually. In this case, I'm just reading it directly from the robot object and using some of the class variables. Now, these two parameters are used to compute our M matrix, which is basically a 2x2 matrix that is used to convert our linear and angular velocity into the right wheel and the left wheel angular velocity, because these are the parameters that we can send outside our algorithm into the robot. And then, because we are using a state machine, as we mentioned in the slides, we have two different states, either point to point or follow the wall, and we're always going to start with the state of point to point. Now you will notice that all of the parameters that I've used here, they are defined inside my alg, because we want to keep track of them over different time steps. Okay, so outside my alg, everything outside this if statement, everything is going to be called in each time step. And the first thing that we need to do is we need to compute our robot pose, and the way that we do so is by reading the value of the encoders, and we pass them into our localization object, and it's going to update our pose. Then we use that pose to compute both the distance and alpha. So the first thing that we need to do is we need to define our goal. Where do we want the robot to go? And in this case, we want it to go to 0.6 and -3, x-axis and the y-axis, y value. S here basically reads the pose of the robot from our localizer object. And then we compute our distance using the Euclidean distance formula, which is defined inside this function distance to point. And we compute our angle between the robot and the goal using the formula that we've seen in the slides. Note that I'm using this function that is called atan2, which is going to return a value between minus pi and pi. And then because we are subtracting also the robot orientation, we cannot guarantee that the angle is always going to be between minus pi and pi. In order to do so, I'm using this built-in function in MATLAB, which is called wrap to 2 pi, which is going to guarantee that the output is always from minus pi to pi. Okay, so far so good. The next thing that we need to do is we need to create our state machine, and in this case I'm using the switch statement. And basically in the switch statement I'm reading my state, and if the state is going to be point to point, I'm going to execute everything that happens here. Otherwise I'm going to go to the obstacle avoidance and execute everything that happens here. So let's fill these two sections right now, and we start with point-to-point navigation. And the first thing that we need to do in point-to-point navigation is basically we are using a bank control for our omega and proportional control, bank control for our linear velocity, and proportional control for our angular velocity omega. And this is what you can see here. Basically, if the distance that we measured here is greater than, let's say, 0.1, this is, by the way, is a value that you can change. This is your epsilon, the first epsilon that we defined in our lectures. And if that's the case, we just our linear velocity is going to be Vmax, and our omega is going to be what we defined as the proportional control by this value over here. Otherwise, if the distance is less than 0.1 or equal to that value, we're going to stop the robot, and we're going to command our simulation or our user interface that we are done, and the whole program is going to terminate. Okay, then after that we need to make sure that we are also looking ahead for any obstacles around us. And one of the first things that we need to do is we need to make sure that our servo motor is pointing at the right direction. And remember from from the slides that the angle of the servo depends on our angular velocity of the robot. So we have our omega, we divide it by the Vmax to normalize for normalization, and we multiply it by our maximum servo angle that is possible. Remember that this value was defined in our initialization over here. I think it's right here. Yep. Okay, and then after that we need to make sure that we change the state from point-to-point navigation into obstacle avoidance or wall following if necessary. And the way that we do so is by looking at the value of the sonar, and if that value of the sonar is less than the safe distance, then yes, we're going to change the state as we change here. But before we change the state, we need to make sure that our servo is pointing at the right direction. And the way that we do so is we have an option: either we turn that servo to the right, completely to the right, or completely to the left. And the way that we make this decision is by looking at its current value. If its current value is positive, we just turn it to the maximum positive. If its current value is negative, we turn it into the the most negative value. Okay, so that concludes our point-to-point state, and let's move forward and fill out the section where we do obstacle avoidance or wall following. And as we've seen in the lectures or the slides, we first define our linear velocity to be the maximum value. Okay, so then we have this, we define this value called distance threshold, which is basically a modified value of our safe distance, and I'm using a bit of geometry by dividing the safe distance by the sine of our maximum servo angle, just to take into account the angle of the servo and making sure that the robot maintains that safe distance to its either right or to its left. Then we use the bang control for our angular velocity, and remember that C value that we talked about in the slides, we just compute it here. And then we have our three different conditions where this value here represents our raw maximum, it's our raw minimum, and this value represents our raw maximum. And please note that we are using the threshold distance that we just computed a few seconds ago. And then finally, we need to make sure that we change the state back to point-to-point navigation if our alpha is less than epsilon 2, and in this case I'm defining it as 15 degrees. Cool. So so this part concludes our state machine, but that doesn't finish our program. The first thing that we need to do is we need to make sure that this linear velocity W and V and the angular velocity omega are converted into the angular velocity of the right wheel and the left wheel, and we can use that M matrix that we define in our initialization. And then after that, all we need to do is we just send the signals to the right motor and the left motor. Okay, now we have finished writing our algorithm. We go to our user interface where we have the robot is at its starting point at 0, 0, 0, and here we have an obstacle represented by this dark object or this dark polygon, and remember that our goal is going to be at 6 and -3, so we are asking the robot to come to somewhere around this region. The first thing that we need to do, we need to write down the control file, and I think it was called drive to a goal. That is correct. And then all we need to do is remember that this is just a simulation, so everything is going to be offline, and then we are basically running the session. So let's see if the robot is getting there. So as we said before, the robot now is just going from point-to-point navigation until it gets too close to the obstacle, when it activates the wall following strategy. So the robot right now is in that particular state, making sure that it maintains the particular distance to that wall, and it keeps doing so until it finds an opening where it can see the goal without any obstacles, and that should happen I think quite soon. There we go. So as you can see right now that the robot is not seeing anything. It terminates the wall following strategy, and it goes back to going from one point to another until it reaches its goal, at which the robot is going to stop and the program terminates. We can do the same thing in reality. So the only difference is that I'm going to start the whole routine by changing or resetting the pose to the origin, and I'm also going to remove the obstacle. This obstacle here is going to be removed. Okay, and then because I'm doing everything in the real robot, I want to make sure that it's connected. I'm clicking on connect to the physical robot, and then we hit run session, and this is what you see in the real robot.